Hello. We're going to be moving on to chapter 12. So this is a new chapter that we're picking up. So this one has to do with carbonyl compounds, in particular the concept of oxidation and reduction in terms of organic chemistry. You probably would have seen it in general chemistry, but that was for inorganic, and so that one is moving the charge, increasing the charge, decreasing the charge on a metal ion. It's a little bit different from the with respect to organic chemistry with that, but it's not too complicated. And then we'll also talk about a little bit about organometallics, in this case organolithium and organic magnesium compounds were also known as Grignards with that. So a lot of these compounds are going to be dealing with the carbonyl group, and if you remember back from the when we were doing naming, right, the carbonyl can be many different functional groups with a lot of different types of properties. It just depends on what's on either side of the double bond. So aldehydes are, you've got a carbon group on one side, you got a hydrogen on the other, but in ketones you got both. Carboxylic acid, OH versus a carbon, ester, carbon on one side, O carbon on the other, and then in an amide you've got a nitrogen on one side and a carbon on the other. So, but you have to remember that these things, because they're sp2 carbons, they're sp2 hybridides. They've got three bond sets around them, right? 1, 2, 3. They're going to be sp2, so they're going to be flat. So they have an unhybridized p orbital that can make the double bond. So, but one of the most important things about the carbonyl is the fact that it's a polar covalent bond, right? So you're going to have this. So that you're going to have a partial positive here, partial negative there. So that's the arrows, but sometimes it's easier to see the deltas. And it doesn't matter if it's a double bond or a single bond, right, or a triple bond or whatever. It's just the difference in the two atoms. Okay? Because when we get to a mechanism, right, what we're going to have is a general mechanism would be having the nucleophile come in, because the nucleophile is going to at least have negative character, but it is going to have a lone pair. The lone pair is going to want to make a new bond with the carbon of the carbonyl, right, because it's partial positive. So we're going to use these lone pairs, going to make a new bond. This carbon can't have 5 bonds, so it is going to be pushing one of these bonds, the 2 electrons, up onto the carbon, or excuse me, up onto the oxygen. Right? So now you've got 3 sets of lone pairs. So one of these bonds becomes a new lone pair set, and that's how all of these things work. Okay. Now, as far as oxidation and reduction in organic chemistry, you can think of it 2 ways. If you're increasing the number of carbon-oxygen bonds, you're oxidizing. If you're reducing the number of carbon-oxygen bonds, it's reduction. So just how do the number of CO bonds change? Now, another way you can think about this is that if you have fewer CH bonds, it's an oxidation, and a reduction is more CH bonds. Because typically what you're doing is you're going to be converting the CH bonds into CO bonds when you oxidize, and vice versa. You're going to be converting the CO bonds to CH bonds in a reduction. That's typically what ends up happening, but it doesn't have to go that way, but that's the most common. Okay, so if you want to think about the oxygen content, right, so you're going to go from 3 CO bonds, right, you got 2 here and 1 there, down to just the 2, right, so 2 CO bonds. If you want to think about right, if you want to think about the number of CH bonds, right, so with that here we've got 1 CH, and here we have 2. Now we are really only going to care about the carbon that the groups are this carbon here that has the CO bond. That's where all the magic is going to happen. If it doesn't have a CO, at least 1 CO bond there, we don't care about it with that. So, but it's always going to be where that carbonyl is, or at least a single CO with it. So, okay. So for here, if you do an oxidation, right, you're converting one of these CH bonds into a CO bond, so you're going to get alcohol. If you want to do it again, you're going to be right? You're going to be going from 0 CO bonds, 3 CH, right? You're going to be going to, now you've got one CO bond, 2 CH. You're going to be converting these, right? Here you've got 2 COs, you do another oxidation, 1 CH right there. And now you've got, in this case, you have 3 CO bonds. Now we can't have a CO triple bond. That would be a carbon monoxide, basically, and that's not going to be particularly stable. So the way that we get 3 CO bonds on a carbon is going to be either a carboxylic acid or an ester. And if you're oxidizing this, you go up to the carboxylic acid. But notice how, again, we're increasing CO bonds by burning the CH bonds. You go from 3 to 2 to 1 to 0. We can't go any further because we don't have any CH bonds. We're like, hey, wait, hold on, there's an H right there. Yeah, but that's an OH bond. It's not, we're looking, oops, this needs to be a CH. We're going to be converting CH bonds specifically, not OH bonds. Okay, so so if you want to go backwards, if you want to go do a reduction, stuff like this, so you can go to primary and secondary alcohols depending on how you want to do it, right? So you can go here, so you burn these two, right? You're going to burn these 2 CO bonds to, now they're going to be, right, 2 CH bonds. There, right? It's 2 CO to 2 CH bonds. So that same thing here. For an aldehyde, right? Again, you're going to be going from so the 1 CH bond, right, to 2. Right? There's 2 right here. This one here, and then going to these 2. If you have a ketone, again, you're going to go from none to 1. Right? There's a CH bond there. So don't forget. So these are all reductions. Now, one of the things is you can't do a tertiary alcohol, right? Because if you had a tertiary alcohol, it would be carbon, 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 CH, or OH here, right? There's 0 CH bonds that we could. So there would be, right, now let's try this again. Right, there are no CH bonds hanging off of that carbon. So there's no fuel to burn to be able to make a new C double bond O. Plus, even if you tried, you would get a ketone. You would get a double bond here. You're not going to break a carbon-carbon bond, so you'd have 5 bonds. So there's a lot of issues with it. So so tertiary alcohols are going to be resistant to oxidation. Okay. So how do we do this? Well, there's two different sources of nucleophilic hydride. We can't use sodium hydride because that is, as it turns out, that's usually that's not nucleophilic. It just acts as a very good base because you're going to make hydrogen gas. Here, I mean, they can make hydrogen gas if you put in if you mix it with a something that has acidic hydrogens, but these are much more nucleophilic. Okay, and so lithium aluminum hydride, LaAlH4. Okay, so this is going to reduce esters, carboxylic acids, aldehydes, ketones. They're going to take it all the way down to the alcohol. With that, so it's going to go all the way as much as it can. With that, but with sodium borohydride, so this one is very similar to it, right? Boron is just right above aluminum in the periodic table. This one can really only convert. It'll still get a nucleophilic attack, right? So you're going to have like that. That's going to come in, attack there, kick that up. You're going to end up making the OH minus, right? Which then gets in the workup, you end up getting an H. This pulls off an 8 when you dump in some water or something like that. Same thing happens here. You come in, you do a nucleophilic attack, that kicks that up to make the O minus, to get the O minus, which then gets converted into OH during the workup. Same thing happens with the lithium aluminum hydride. Now the thing is, yes, so that's all this is saying, is that you got a hydride here, and actually you have 4 hydrides for either borohydride or aluminum, for aluminum hydride. So with that, so one of these molecules can reduce 4 of them. Okay. Now the thing is, the lithium aluminum hydride was saying it's a lot more reactive, so it can convert pretty much any C double bond O down to its alcohol. But sodium borohydride is much more selective. It can just do ketones and aldehydes. But that provides some selectivity for this. So for example, if we had this molecule, okay, with that, so we have lithium aluminum hydride, so we have a ketone here, we have an ester here, so both of those are going to get reduced. So what you're going to end up with is, so there's that. Now the esters end up as alcohols. So this carbon here, that gets cleaved, and this C double bond O ends up getting turned into the alcohol. Okay, so you get this plus OH, like that. Okay. Now for this one here, we have the ketone and an ester, but sodium borohydride isn't powerful enough to react with the ester, so you're only going to get reduction here. So the ester is going to remain untouched. So it's only going to be the ketone that gets reduced down. Okay. So there we go. Hey, we got them right. Okay, so we can also oxidize alcohols up to C double bond O's, right? So for primary alcohols, right, they can go from an aldehyde, from the primary alcohols can go to the aldehyde and the carboxylic acid, right? Because we have two CH bonds that we can convert to 2 new C double bond O's. So we go from 1 to 2 to 3 C double bond O's because we have 2 of these. Secondary alcohols, they only have the single CH bond, so that means that we can only increase the number of CO bonds by 1. So you go from a secondary alcohol to a ketone. And again, tertiary alcohols, they don't have the CH bond, so they are going to be resistant to oxidation. So how do we do this? So there's 2 different mild ways to do it, and then there's some more powerful ways. So the Swern oxidation, that only converts 1 CH bond to 1 CO bond, and it stops, full stop. So for here, right, we're going to be going from 2 CH bonds, right, 2 CH, into just the 1. Okay, Swern oxidation is a really nice way to doing this because it stops at the aldehyde. One of the problems with a lot of different types of oxidation techniques is the aldehyde is usually quite reactive, and then you can go onto the carboxylic acid. But for here, it stops. The mechanism is such that it stops at the aldehyde, and that's it. Again, and then for here, right, we have 1 1 CH bond, right? Oh, forgot to put this on here. 1 CH, right? Going to no CH, but we only go 1 step. Well, that's the only way it can go, but still, it would only go 1 step up, okay, from 2 to 1, and then 1 to none. The other way that we can do, so this is the mechanism. It's kind of a crazy mechanism. I'm not going to go through it. But it does work quite well with that, and it's working because it produces dimethyl sulfide, which is what they put in natural gas so you can smell it, and it stinks. Even if you do it in a hood, you usually smell it. But it is a very cool mechanism. The other way that you can do this is pyridinium chlorochromate, or PCC, with that. So it does contain chromium 6. So if you're going to do an oxidation, typically you do a Swern oxidation. It's much milder, and you don't have to worry about chromium compounds. But it does the same thing as what the Swern does. It converts 1 CH bond into 1 new CO bond, and that's it. It stops there. Now, if you wanted to go all the way, you can use chromic acid with that. So those primary alcohols are going to be taken all the way up to the carboxylic acids. Secondary alcohols going to be taken up to ketones. You convert all the available CH bonds that are on the carbon that has the alcohol in it into new CO bonds. Okay, but again, you're going to be working with chromium 6 and manganese 7. So these are going to be reactive. Now the difference between chromic acid and PCC is that this one is basically poisoned by the pyridine. It's very similar to when we were talking about the hydrogenation, where if you had the just a regular hydrogenation, it would, on a triple bond, it would take it all the way to a single bond. But if you did a Lindlar catalyst or some sort of poisoned catalyst, it would only stop at the double bond. Same thing here. We're basically poisoning the chromium so that it only has powerful enough to oxidize once, as opposed to all the way. So it's a very similar concept. Okay. So if we want to predict the products for these reactions, right? So here we've got potassium permanganate, right? We have a primary alcohol, right? So we have two CH bonds here, so that means we're going to convert both of those into new CO bonds. So the way that we get 3 CO bonds onto a carbon is through a carboxylic acid. There we go. Now for the Swern, again, this one, it has 2 CO bonds here, or 2 CH bonds, but it's only going to be converting one of them. Okay, so you're going to end up with this. So you're going to make an aldehyde. So you're going to go from 1 CO bond to 2, and you're only going to burn by burning only one of the CH bonds. Same thing going here, right? So that's but here, right? This is a tertiary alcohol. So that there are no there aren't any CH bonds to oxidize. Stuff like that, and so this one is no reaction because it's a tertiary alcohol. Okay. Now for the organometallics, right? Just like with the lithium aluminum hydride and sodium borohydride, right, we want to make nucleophiles, and this is a nice way of doing it. With that, so if you have a bromide or a chloride or an iodide, for that matter, you can. If you put in sodium metal, so you get a chunk of solid lithium and throw it in there, it will actually displace the lithium. And it works like this. So it's an organometallic bond, but you can sort of think of this as CH3, CH2, 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 and then this one has, come on, oh, there we go. This plus lithium. So you can think of it as having a set of lone pairs. Okay, so these are actually a set of lone pairs here. So what it ends up being is basically a stabilized carbanion and stuff like that. And so for that, you can use it for doing all the other things a nucleophile can do. Okay. So you can either do that with the bromine, right? So so we don't need the bromine here, right? Because the carbon's going to have a negative charge. The lithium has a +1 charge because it's an alkali metal, right? So everything's balanced out. But if we get to the magnesium, it does the same. It does the exact same thing. Is that here? It's down here, right? Remember, this is basically like having a. Oh, come on. Set of lone pairs there and a negative charge. Magnesium, because it's an alkali earth metal, right, is going to have a +2. So that's why we have to keep the, if this is a bromide, keep this around in order to be able to balance out the charges, right? This -1, magnesium wants to be a +2, so we need to have the bromide or whatever the halide stick around to balance out the charges. Now it's a lot more complicated than that, but I always thought that was the easiest thing to do. And so these can act just like carbanions, right? So they can work as a base, right? So if you dump it into, you throw in your Grignard reagent, which is the magnesium one. If you dump it into something with an alcohol, all that's going to happen is it's going to rip that away. It's going to act like a strong base. There you go. But you can use them because they're quite powerful bases. You can use them instead of sodium amide to rip off the hydrogen on a terminal alkyne to get that. To get this, to make this what is it, this nucleophile. Now, and the nice thing is you usually just end up with an alkane at the end, stuff like that. So this is going to be completely unreactive, and so this is going to be your only nucleophile. So the other thing that you can do, right, so that is you can do everything that a regular nucleophile can do. So with that, so if you have this one here, right, so you have a partial positive, so the oxidation, it's partial positive, partial negative. So the negative charge on this carbon is going to come in and make a bond here, right? It already has its 4 bonds, so it's got to break it open. And by doing that, you not only make this new bond here, you give this a new set of lone pairs, which is always good. You relieve the ring strain here. So this is these oxiranes are very, very powerful. And so for here, you've got again, you've got a lone pair here. You can sort of think of it like that. It's going to attack there, kick up, and then after the workup, you're going to end up. So these 2 carbons here are these 2 carbons there. Okay. So, and again, they can work just like any other nucleophile. If you want to do an SN2 attack, right? So this is just, this is just an SN2, right? You've got a carbon nucleophile. Right, you got lone pairs here, if I can draw them in, right? Negative charge, that's going to attack here, kick that away, and you're going to make you're going to make the new carbon-carbon bond. You're going to make this new bond there, stuff like that. So in lithium bromide. So, and that's how all of these work. So if you had a C double bond O, right? So again, you're going to have partial positive here, partial negative. So the negative charge on this one is going to attack here, move that up. So and then during the workup, right, you're going to make the OH. So here's our negative charge right there. So it's going to attack right there, right? Because this is a partial positive, partial negative. Push that up, right? So you're going to end up with, right? So here's the it's going to be an O minus, but during the workup it's going to turn into an OH, right? You're going to have the hydrogen here, and then we're going to have our new 1, 2, 3, right? 1, 2, 3, like that piece there. So this is where the Grignard originally was, right? So we're going to make that new bond. Same thing here, right? So the negative charge is right there, right? Remember, partial positive, partial negative, right? So it's going to attack there. It's just an SN2 attack. And kick that away. So you're going to end up with OCH3. So this 3 carbon piece here, right there, that plus Cl minus. Well, yeah, and then Li plus. There you go. So if you wanted to make alcohols from Grignards, if you want to make primaries, right, you can either use formaldehyde here. It's just going to add a 1 carbon piece, but again, right, you're going to get an attack there that's going to kick up, right? So this 1 carbon here is that 1 carbon there, and you're going to make a nice little primary alcohol. If you want to add 2 carbons, right, so these 2 carbons here, right, are going to be those 2 carbons there. So you can do oxiranes. If you want to do secondary alcohols, you would just use, say, something like acetaldehyde, so some sort of aldehyde, right? Because again, you're going to be attacking here, coming up, and those 2 carbons there, those 2 there, but again, it's on the inside, so the OH is going to be you're going to make the secondary alcohol. If you wanted to make the tertiary alcohol there, then you're going to need a ketone. Right? So with that, so again, you're going to have this there, tack there, kick this up, right? So with that, but again, you already have those two carbons hanging off of that one. You're adding a third carbon-carbon bond at that position there, so you're going to end up with the tertiary alcohol. Now, the last thing, this is more of a concept. You don't necessarily need to know this, something like that. But the problem is, if as the molecules get more complicated, right, you have to take into account that if you want to react at one end, at one particular functional group, are the other functional groups going to react with it? Now, hopefully they won't, but sometimes they do. So how do we get around that? Well, so for example, if we had if we want to take this molecule into this one, right, what you would normally think is you can make a magnesium bromide and an acetaldehyde to add your 2-carbon piece here, make the secondary alcohol, no problem. But if you come in here and make the Grignard, this right here is going to act as a base and come in and just rip the OH off, and you're just going to end up with this, and then the hydrogen that was originally there is just going to end up over here, because you're going to get a really nice acid-base reaction. So what you really want to do is if you want to do this reaction, you need to make that particular one unreactive. And so what you have to do is first do what's called a protecting group. And you're going to make this into a temporarily unreactive. Okay, so in this case, you would add silyl chloride, some sort of silyl chloride. You're going to make this, and now it's a silyl ether. Now those are unreactive towards the Grignards, stuff like that. And so you can do the normal Grignard stuff, put this together. Now we need to remove that, and typically you remove it with fluoride. And that will cause because the silicon fluoride bond's really strong, that will cause it to break that bond and release the OH form again. So this is a way of temporarily sort of blocking blocking a reaction at one particular spot while you go and do something else, something like that. So it's one of the things where it's nice to be able to design your synthesis so you don't have to do it, work with them, but sometimes that's not practical, something like that. So, and there's a huge number of these things, there's all sorts of books and things like that on that. So I think that's it. Good luck.